We're continuing with Chapter 3 in the geometry textbook. In this video, we're going to go through the third section, which is on isosceles triangles. So in this section, we're obviously going to learn about isosceles triangles, but we're also going to be introduced to some important auxiliary lines that we use to analyze triangles, not just in this section, but in upcoming sections and chapters, like the angle bisector and the median and the altitude and the perpendicular bisector. All right, so it says, in an isosceles triangle, the two sides of equal length are legs, and the third side is the base. So yeah, we've already talked about what an isosceles triangle is. We already know what an isosceles triangle is. It's a triangle that has two congruent sides, two sides of equal length. So a scalene triangle has no sides of equal length. An isosceles triangle has two of the three sides are of equal length, and an equilateral triangle has all three sides of equal length. Okay, so again, we know what an isosceles triangle is coming into this section. So now it says that, so with an isosceles triangle, the two sides of equal length we call legs, and the third side we call the base, as shown here. The point at which the two legs meet we call the vertex of the triangle, and the angle formed by the legs and opposite the base is the vertex angle. The two remaining angles are base angles. So we call the two equal length sides legs, the third side the base. We call the point at which the two legs meet, that vertex, we call that the vertex, and the associated angle the vertex angle. And then the other two angles we call base angles. This is for isosceles triangles. Okay, so if AC is congruent to BC in this figure here, AC congruent to BC, then triangle ABC is isosceles with legs AC and BC. AC and BC with base AB. And then vertex C, vertex angle C, and then base angles at A and B. Okay, now, but it points out that with these two sides being the legs, that it's not always the case that the base side is like the bottom side, and that makes sense. That's what we're seeing when it comes to comparing triangles, congruent triangles, etc. Really dealing with any figures in geometry, they could be oriented in different ways. The orientation is irrelevant. It's more of recognizing what kind of figure you have outside of the orientation. So, you know, this is isosceles, right? It's kind of on its side. You could say the base side is over here. Here are the two legs. Here's the vertex angle. Here's the base angles. You have to be able to, for everything we study in geometry, you have to be able to identify everything we talk about if you're looking at figures in whatever the orientation may be in 3D space. Okay, helping lines known as auxiliary lines are needed to prove many theorems. To this end, we consider some of the lines that may prove helpful. Yeah, so auxiliary lines are really important for analyzing any kind of figure in 2D or 3D in certain circumstances. So here we're going to take a look at the important auxiliary lines that we use to analyze triangles. And remember, we talked about auxiliary lines before. These are just lines that we add to a figure for purposes of analysis. Okay, and it was important that when we add a line like this, an auxiliary line like this, it needs to be a unique line. And then, but furthermore, it also, so it can't be under constrained. But at the same time, it also can't be over constrained. In either case, it doesn't make sense if you add an auxiliary line that's under constrained or over constrained. For example, if we come here, we talked about how we could add an auxiliary line that goes through point A and is parallel to line BC. That would be a unique line. Okay, but we couldn't just say that we're going to draw a line that goes through point A. That's all we say. Okay, we're going to draw a line that goes through point A, and then draw this line and then start analyzing. Well, what line is this? There's an infinite number of lines that go through point A. So you need more information. Okay, so that's an under-constrained case, but there's also over-constrained cases. You can't, we couldn't say, okay, we're going to draw a line that's parallel to AB and also perpendicular to AC, okay? Because look, I mean, that's not going to make sense. That's too many constraints. Now, we could do this if we made some other side statements that justified why, look, this line can absolutely be parallel to AB and perpendicular to AC. We could do that. But what I'm talking about is if we're just talking in general, in generalities, we couldn't just make a statement like, okay, this line is going to be perpendicular to one line and parallel to another line, and without making any further, stating any further information. We can though, it is fine to, in complete general, say that, look, we're going to add a line that's parallel to one line and passes through a point that's not on that line. Right? We could make that statement in complete general, and that makes sense. We don't need any more information. Look, we're drawing a line that goes through this point here that's parallel to line BC. That's it. That's all the information we need. But again, saying that in general, just saying that, okay, we're going to draw some line that's parallel to AB and perpendicular to AC. Well, okay, but is AB perpendicular to AC? We need more information. We can't just state that in general. So that's the over-constrained case. Okay, so now with that then, let's talk about that there's four important auxiliary lines that we use to analyze triangles. And these are all unique lines. Okay, we've got the angle bisector, the median, the altitude, and the perpendicular bisector. These are the four line types. And for each triangle, there's three separate ones of these. Like for each triangle, there's three unique angle bisectors, there's three unique medians, there's three unique altitudes, and there's three unique perpendicular bisectors. And this is, we're talking in complete generalities here as far as this works for any triangle. This is the case. Yes, in some special circumstances, for certain special triangles, it might be the case that angle bisectors and medians are the same line. And maybe in some cases, an altitude is the same as an angle bisector or whatnot. But in general, they're unique. In general, all of these are completely unique. Okay, so the angle bisector, you can draw an angle bisector that originates from any one of the three vertices of the triangle. And it's simple. It just bisects the angle it comes from, the vertex angle it comes from. That's it. It splits it into two equal angles. That's it. And you can draw this as a ray that goes all the way through the opposite side, or you could leave it as a line segment that just terminates at the opposite side. That's the angle bisector, originating at any one of the three vertices of a triangle. Bisects that vertex angle. Okay, now you also have what's called medians. Medians originate from any one of the three angles of a triangle, but they don't bisect the angle they come from. They go to the midpoint of the opposite side. So they bisect the opposite side. See, the midpoint here of AC. Here it goes through the midpoint of AB over here. Okay, so that's the angle bisector, that's the median. Now we also have what's called altitudes. These are they originate at any one of the vertices of a triangle, and they are perpendicular to the opposite side. So like that, or like that. Okay, and now finally we've got what's called perpendicular bisectors. These lines are perpendicular to and bisect the sides of a triangle. Okay, now but notice here though we can't say that a general perpendicular bisector is going to start at a vertex, because that would be over constrained. Because look, I mean, here's This AE is perpendicular to this side, but it certainly doesn't bisect that side, right? So saying that both those constraints are present at the same time, well, all three of those constraints, meaning that it's perpendicular to it, bisects, and it starts at a vertex, that's over-constrained. All three of these, if you think about it, all three of these, the angle bisector, the median, and the altitude, they're perfectly constrained in the sense of how we constructed a line that's parallel to BC and goes through point A. That was perfectly constrained, right? It's one unique line, not under-constrained, not over-constrained. Each of these were not under-constrained or over-constrained. But if we added one of these constraints to like the other, if we said that, okay, we have the angle bisector and it's also the median, it passes through the midpoint of the opposite side, that would be over-constrained in general. Yes, in certain special cases that might happen, but in general, for any general triangle, no. So these are all perfectly constrained. So for this auxiliary line to be perfectly constrained, we remove the constraint that it has to start at one of the vertices. We just say that in general, it's perpendicular to and bisects the side of the triangle. So you can see there's the perpendicular bisector of BC. All right, now here is the perpendicular bisector of AC, and here is the perpendicular bisector of AB. Okay, now just to further illustrate that these lines are unique, we can draw a triangle over here. Okay, so in general, we're going to have, coming from vertex A, we would have an angle bisector. You could do an angle bisector coming from each angle. Okay, we would have a median coming from each vertex. Okay, we would have an altitude coming from each vertex, perpendicular to the opposite side, and we would have a perpendicular bisector that doesn't originate at a vertex. So it would go through where the same spot where the red line bisects. So it would bisect and be perpendicular. Okay, so, and again, I just want to stress that in general, in complete general, all of these lines, all this would be what? 12 total lines? Yeah, 12 total lines. In general, all of these are separate and unique. In general. But there are special cases where they do end up being the same line. Maybe for an isosceles triangle, this might be the case, right? With the symmetry, two legs being equal, we'll see. Maybe with the isosceles triangle, some of these lines do match up, but in complete general, they're all unique. Okay. In figure 3.25, they show, so if we come here, they show the four auxiliary lines that are associated with this side of the triangle BC. So associated with any side of a triangle, you're going to have the three auxiliary lines that are coming from the vertex that's opposite that side. So coming from vertex A, you have they show the altitude here, the angle bisector here, the median here, and then you'll also have the perpendicular bisector of that side as well. So these are the four auxiliary lines associated with this side BC. Okay, so now some attributes of these auxiliary lines are that, so, all right, if we think about the altitude line, so this is coming from the vertex going to the opposite side, perpendicular to the opposite side. In some cases, an altitude can lie in the exterior of a triangle. Okay, so let me bring in this figure over here, figure 3.26. Okay, so for example, this obtuse triangle here, if we think about the altitude that goes from vertex R to the opposite side, well, this is a little bit different because if we can't construct an altitude going from vertex R to side ST. If we stay inside the triangle, the interior of the triangle, we can't do it, right? So, but there still is an altitude. We just virtually extend that side. And in that case, RH is the altitude. Since it's perpendicular to the extension of side ST. Okay, so that's something to note about altitudes. Okay, now next it talks about how later we're going to learn how we can associate the altitude of a triangle with the area of that triangle by the formula that the area of a triangle is 1/2 times the base times the height. So what they're saying is that you can take any of the three altitudes and the base that's associated with that altitude, and so then you take the length of that base, the length of that altitude, multiply those two together, divide that by 2, and you have the area of the triangle. And so for the case of this triangle, it would be 1/2 times the length of RH times the length of ST, not the length of HT. But we'll talk about the specifics of this later. Okay, but coming back to the characteristics of these auxiliary lines, so it's you can see that you can have an altitude that in some cases be on the exterior of a triangle. But okay, what about the angle bisector and the median? Well, if you think about it, in those cases, those are always going to be on the interior of the triangle, no matter what. And this makes sense because, like, if we come to this triangle here, how could an angle bisector or a median not be on the interior of the triangle? Because for the angle bisector, you're bisecting the angle associated with the vertex, right? So like you're going to have to be going down the center of into the center of that triangle, and it's similar to the median. You're going to the middle of the side that's opposite the vertex. So like it's just by definition, you're always going to be in the interior of the triangle. Okay, now if we come here, some more attributes of these auxiliary angles. It says, so each triangle has 3 altitudes. Okay, so we're talking about altitudes at the moment, even if they're on the exterior. 1 coming from each vertex. As shown for triangle ABC in figure 3.27, the 3 altitudes seem to meet at a common point. Interesting. So I wonder if this is the case for any general triangle, that all of the altitudes are going to meet at a common point every time. You might say, well, wouldn't they have to meet at a common point? Isn't that a given? No. We could have lines. Maybe one altitude comes here. Maybe another altitude comes here. Maybe the third altitude comes here, right? Yeah, they have to intersect, obviously, but they don't have to all intersect at one point. But in this case, it looks like they do. So I wonder if it's the case that no matter what the triangle is, in general, the altitudes are going to meet at a common point. And perhaps even the medians are all going to meet at a common point, and the angle bisectors. But we haven't stated anything official, though. It just seems to be the case that for this triangle that the altitudes all meet at a common point. But this is just one triangle, and we're just looking at this visually. I mean, let's come to this triangle. So here's one of the altitudes. Okay, so another altitude would be like that. Okay, so we need to extend these. Okay, now extend that one. So there's it's perpendicular here to this side. So yeah, it looks like they meet at a common point here as well. So maybe it is going to end up being the case. We'll be able to prove that all altitudes of any given triangle are going to meet at a common point. And same for the medians and the angle bisectors. But we'll see. We haven't stated anything official yet. All right, we now consider the proof of a statement that involves the corresponding altitudes of congruent triangles. Corresponding altitudes are those drawn to the corresponding sides of congruent triangles. So corresponding altitudes, right? So we talked about it's with congruent triangles, there's corresponding features. You could have any kind of corresponding feature. It's just the same feature on the 2 separate triangles that could be that are in general going to be oriented completely differently in 3D space. You're just saying, okay, they're the same triangle, they're congruent, But since they're oriented completely different in 3D space, then it's useful to match up, okay, what corresponds to what? What's the equivalent feature on the other triangle? And so it's common sense, even though that they have to prove this officially here mathematically. They need to prove this. This theorem, from just an intuitive standpoint, corresponding altitudes of congruent triangles are congruent. That's common sense. It's the same triangle. Every corresponding anything is going to be equivalent. It's the same triangle. Corresponding altitudes are going to be equivalent. Corresponding medians, corresponding perpendicular bisectors, whatever. It's the same triangle. It's just oriented completely different. And then with that, a corresponding feature is just the feature that corresponds to that feature on the differently oriented triangle. It's the same feature, though. It's the same thing. So they're congruent. Okay, but still, mathematically, they go through an official proof of this theorem here. All right, now it says each triangle has 3 medians, one from each vertex to the midpoint of the opposite side, as the medians are drawn for triangle DEF here. It appears that the 3 medians intersect at a point as well. That's interesting. So there you go. It looks like it's going to be the case that, in general, the medians and the altitudes and the angle bisectors are going to meet at a common point for any general triangle, which is really interesting. Okay, they do the same thing for the angle bisectors, and it looks like they meet at a common point. But again, these two here are just a particular case for one type of triangle where they happen to meet at a common point, and we're just looking at this visually. Maybe if you zoomed in extremely close, they don't intersect. So we have to prove this officially, that they actually do meet at an exact point for any general triangle. Okay, but now what about the perpendicular bisectors? Maybe those don't meet at a point. Those are kind of different, right? But it looks like those do as well. Here they give an example. Okay, the angle bisectors, like the medians of a triangle, always meet in the interior of the triangle. However, the altitudes, like the perpendicular bisectors of the sides, can meet in the exterior of the triangle. So yeah, let's come back. It makes sense that the angle bisectors and the medians are going to have to meet and just in general be in the interior of the triangle. Okay, but we saw how it can make sense that in some circumstances an altitude can be on the exterior of the triangle, and therefore all the altitudes could meet on the exterior of the triangle. But what about the perpendicular bisectors? Well, those in general you're going to draw on the exterior of the triangle. Some portion is going to be on the exterior of the triangle, and in some cases it's going to, all of those lines are going to kind of converge on the exterior of the triangle as well. Okay, but now these intersections of angle bisectors, medians, altitudes, perpendicular bisectors of triangles, we'll come back to this in a later chapter. We'll look at this in a lot greater detail in a later chapter. Okay, so next it says, in the figure below, the bisector of the vertex angle of isosceles triangle ABC is a line of symmetry for triangle ABC. So, okay, here's triangle ABC. They're telling us it's isosceles with vertex angle B, so that means these are the two legs. They're congruent. Okay, and they're saying that if we add in the angle bisector auxiliary line coming from vertex B, then this line is a line of symmetry for this entire triangle. So that's interesting. Is that just for this specific isosceles triangle or for any isosceles triangle in general? So to think about this, we can look at this theorem here, which says that the bisector of the vertex angle of an isosceles triangle separates the triangle into two congruent triangles. Well, yeah, in that case, if this theorem is true, then the fact that this is a line of symmetry makes sense, because it's saying that the angle bisector coming from the vertex angle of an isosceles triangle separates the triangle into two congruent triangles. Well, okay, if that's the case, then this triangle ABD here and CBD have this common backside leg here. That's the angle bisector. Okay, but now if these two triangles are congruent, then just the triangle on the left is a flipped version of the triangle on the right, flipped about this line of symmetry. So yeah, that's interesting. Okay, let's go ahead and prove this theorem. So, all right, in this theorem, we're given that we have an isosceles triangle So let's imagine we just draw an isosceles triangle here, just a general isosceles triangle, and we'll have the vertex angle be at B. So that means that these two sides are congruent. Okay, and now the statement is that the bisector of the vertex angle, that auxiliary line, is going to separate this triangle into two congruent triangles. So this is completely general now. We're adding in this angle bisector line here. So we're saying that angle 1 is congruent to angle 2. We can do that. We can add this auxiliary line in. This is going to be a unique line here that's not over-constrained or under-constrained. But with that, then, to make that truly be the case, the idea is we've made this constraint here, but now we can't make any statement about what's going on around here. If point D is the midpoint of line segment AC, we have no idea. Or like the angle, this angle right here, CDB or ADB, I mean, maybe it's perpendicular. We have no idea. The only constraint we made was that it's the angle bisector. Okay, so there you go. That's what's given. That's the only information we're given. With just this information, can we prove that these two triangles that are created here, this triangle ADB and CDB, are congruent? Well, okay, let's see. We have a common side here, BD. And yeah, there you go, side angle side. So we can state by side angle side that these two triangles are congruent. So yeah, that theorem is true. And so yeah, it makes sense that this angle bisector line of an isosceles triangle, the angle bisector that comes from the vertex angle of the isosceles triangle, is a line of symmetry. And what's interesting here is that what we can also see is that, so if these two triangles are congruent, that means these two sides are corresponding, they're congruent. Okay, these two angles are congruent here. Those are corresponding. And then these two angles are corresponding, so they're congruent, but they in total, they make a straight angle, so this is perpendicular here. So in this case, the angle bisector and the median and the perpendicular bisector and the altitude, all four of those lines, coincide with one another in this special case here. In general, that's not the case, but in this case, they do. So that's really interesting. Now, note, though, this is just for the isosceles triangle. It's just for these auxiliary lines coming from the vertex angle. It wouldn't be the case necessarily. We haven't made any statement about like these lines coming from a base angle. You would assume that they all wouldn't coincide, but we haven't talked about that. This is strictly for the lines coming from the vertex angle of an isosceles triangle. Okay, so now next what they talk about is they give a summary of the idea of over-constrained, under-constrained, and properly constrained auxiliary figures that you bring in, that we talked about earlier in the video. And they give an overview of that here, because what we're going to be doing in upcoming proofs is that we're going to see how for a lot of proofs, you're going to have to add in your own auxiliary figures. It's not going to be laid out for you in the theorem all the time, to where you're going to know exactly what auxiliary line you need to be adding. So it's really important that you understand exactly what a properly constrained auxiliary figure is. Okay, and so they just go through this again, everything we just talked about a few minutes ago. So the term that they're using is determined. So you can say constrained or determined. So over-constrained, under-constrained, properly constrained, or over-determined, under-determined, properly determined, or just determined is what they say. So here we've got this, you draw a line that originates at a vertex of a triangle and is perpendicular to the leg opposite that vertex. In complete general, this is properly constrained. You can make this statement here in the same way that you could make a statement that I'm going to draw a line that goes through point A and is parallel to line BC. I don't give any less constraints, don't give any more constraints. You can make this statement and draw this line in. Okay? But like here, you couldn't say that I'm going to add this line that goes from vertex A and passes through the opposite side BC. Well, which line? That's under constrained, that's under determined. Which line? There's an infinite number of lines that do that. So it's not enough information. You can't add an auxiliary line and just say that. Okay, now the last example is the overdetermined example, or overconstrained. If you're going to say that you're going to draw a line from vertex A that's perpendicular to and passes through the midpoint of the opposite segment BC. Well, that's too many constraints. For a general triangle, you can't make that statement. Now, if you gave more information, if you specified, like we just saw, if you specified, okay, I've got an isosceles triangle, and I'm drawing, now I'm going to add an auxiliary line that starts at the vertex angle of the isosceles triangle and passes through the midpoint and is perpendicular to the opposite side. Well, you can add that auxiliary line because in addition to adding that auxiliary line, you'd make the statement that you'd state this theorem. Look, I can add this auxiliary line because I have an isosceles triangle and I'm drawing this line from the vertex angle of the isosceles triangle. That would be properly constrained, but just giving a general triangle in complete general and making a statement like, I'm going to draw a line from vertex A that passes through the midpoint of the opposite side and is perpendicular to the opposite side, that's overly constrained. You can't make that statement in general without some additional information given. Okay, so again, it's really important to understand that this concept of properly constrained figures in general, but specifically here where we're focusing on these auxiliary figures that we're going to be adding to figures to help us prove theorems or just analyze the problem we're dealing with. Okay, so for example, this theorem here says that if two sides of a triangle are congruent, then the angles opposite these sides are also congruent. Okay, so let's draw a general triangle here. And now we're given that two sides of this triangle are congruent, so it's an isosceles triangle. That's the definition of isosceles. So let's say that MP and PN are the legs. So they're congruent. So we have what we're given is that this is isosceles by definition, and we've chosen the legs. That's all we're given. And now with that, we want to prove that the sides opposite these sides, the angles opposite these sides, which we know are the base angles, are congruent. That's it. So with just this information given, we need to add our own auxiliary line here to prove this theorem. It's not laid out for us as simply as it was before. We have to make the decision on the auxiliary figure that we're going to add ourselves to analyze this problem. Now, this is actually a pretty simple case here because based on the theorem we just talked about, we know that it would be smart to go ahead and add the angle bisector coming from the vertex angle of this isosceles triangle. Okay, now this is a pretty simple case. You can think about it in other situations. It might not be as clear which auxiliary figure you want to add, auxiliary line or figure you want to add. You might add a certain figure, analyze the problem, and realize this didn't really help, and then you add another figure and just keep working with it. Okay, but based on the previous theorem, we want to add this angle bisector here. Okay, so now with that, then we know based on the previous theorem that, so if this is point Q, we know that triangle MQP is congruent to triangle NQP. That's what the previous theorem was all about. So we could, if we were going through the official proof, we could make that statement then based on the previous theorem. And then from there, we know that with congruent triangles, corresponding features are congruent. So M corresponds to N, right? Because we have triangle MQP is congruent to triangle NQP. M corresponds to N, so these two angles are congruent. And there you go. And note that that was completely general for any isosceles triangle. That was completely general. Okay, so now it notes here that, we could have chosen to add a different angle bisector to analyze this problem. Maybe we added an angle bisector coming from angle M here. And then, but that wouldn't have worked. That wouldn't have allowed us to prove the theorem. Now, again, it was pretty obvious not to add that angle bisector, but they're just trying to make the point that for in other cases, it's going to be a little more difficult to figure out what auxiliary figure you need to add. Do you add an angle bisector, or maybe do you add a perpendicular bisector or a median? Maybe you're confident on what vertex you want to be adding an auxiliary line from, but maybe it's confusing as to, well, which auxiliary line should I add? Okay, so this example says, find the size of each angle of the isosceles triangle shown in figure 3.32 on the next page. So here's that figure. If the measure, or part A, the measure of angle 1 is 36 degrees. Okay, well, if that's the case, then we can see that that's the vertex angle. These are the two congruent sides. That's the vertex angle. And we know that, based on the previous theorem, that these two angles are congruent. So if we call this angle x and this angle x, then we can say that 36 degrees plus x is 2x, is going to be equal to 180. Now just solve for x. Subtract 36 from both sides. Divide both sides by 2. X is 72 degrees. Okay, part B says, what if the measure of each base angle is 5 degrees less than twice the measure of the vertex angle? So if each base angle is x, then they're saying that the measure of each base angle, x, is equal to 5 degrees less than twice the measure of the vertex angle. So if the vertex angle is y, then you take twice the measure of the vertex angle and 5 less than that. That's what x is equal to. So, okay, we can replace x with 2y minus 5. And now we can sum the angles to 180. So what is 2y minus 5 plus 2y minus 5? That's going to be 4y minus 10. Okay, plus y is equal to 180. Okay, so 5y is equal to 190. Divide both sides by 5. So we've got, let's see, 190 divided by 5. It's 38 degrees. So y is equal to 38 degrees. But what's the measure of each base angle? So what is 2x is equal to 2y minus 5. So 38 times 2, 76. 76 minus 5 is 71. That's the measure of each base angle. Okay. Now, this next theorem is the converse of the theorem that says that the base angles of an isosceles triangle are congruent. So in this case, the theorem is that if two angles of a triangle are congruent, then the sides opposite these angles are also congruent. All right, so we're given that we've got some general triangle and two of the angles of the triangle are congruent. So we can orient this triangle to where those two angles are at the bottom here. So we make the side that's included between the two angles be horizontal. Right, we could take any general triangle and put it in this configuration here with these two congruent angles. Okay, so that's all we start with, some general triangle like this. Can we prove that this must mean that these two sides are congruent? Well, to do this, we want to add an auxiliary line coming from V here, which isn't like a vertex angle or anything. We don't know what V is. All we know is that these two angles are congruent. So, yeah, now we need to make a decision. Do we add an angle bisector? Do we add a median? Well, what they do here, as you can see, is they add a perpendicular bisector. Or no, just a perpendicular, sorry. They add an altitude. That's it. In general, that's the only statement we can make here. That this line is perpendicular, it goes through V and is perpendicular to TU. This is an altitude. We add an altitude. We can't make any other statements about, okay, it bisects this angle or it's the median. We can't say anything like that. All we can say for sure is that it's properly constrained because we've added, it's going through point V and it's perpendicular to TU. It's an altitude line. That's it. All right, well, that means we can see that it's going to be perpendicular in both directions here. Okay, now let's see. Comparing triangle T, this is point P here. Comparing triangle TPV to triangle UPV, we've got, so a common side here. Okay, we've got angle, angle, side. right? Because it's like these two angles are going to have to be congruent because the other two angles are congruent. So angle, side, angle. So the two triangles are congruent, which proves that these two corresponding sides are congruent. So there you go. Okay. Now, what we can do next is we can use all of these theorems that we've just proved about isosceles triangles to make some statements about equilateral and equal angular triangles. So we're going to state some corollaries here. Remember, a corollary it's like a theorem but based on another theorem, so we call it a corollary. So based on these theorems that we've just talked about, these different theorems that we talked about with isosceles triangles, we can state some corollaries that these two corollaries that relate equilateral and equal angular triangles. So remember, an equilateral triangle is talking about the side lengths. So scalene triangle means that all the side lengths are different lengths. Isosceles means that two of the three are the same length. Equilateral means that all three of the sides are the same length. And then if you have an equal angular triangle, that means that all the angles of the triangle are the same measure, which in that case, because we have the constraint that all the angles of a triangle sum to 180, that means any equal angular triangle is the angles are going to measure 60 degrees. Has to be. Okay. But up to this point, an equilateral triangle and an equal angular triangle were in general two separate triangles, as far as we knew. All right, but we can use these theorems that we've just proved for isosceles triangles to show that equilateral triangles and equal angular triangles are the same triangle. They have to be the same triangle. If you have an equilateral triangle, then you must have an equal angular triangle. If you have an equal angular triangle, then that means you must have an equilateral triangle. And that's what these two corollaries state. An equilateral triangle is also equal angular. An equal angular triangle is also equilateral. So like if you find that all of the angles of a triangle are 60 degrees, it's equal angular, then it has to be equilateral as well. You can't have one without the other. And so what's interesting to think about is here they've got an equilateral triangle drawn with an auxiliary line coming from each vertex. And so what we talked about with isosceles triangles, how the angle bisector coming from the vertex ends up coordinating with the median and perpendicular bisector and altitude. All those lines are the same line. We haven't officially proven that yet, but we could see that that's going to be the case because the two triangles are congruent. So look, we drew this initially as the angle bisector, okay? But now we didn't know, we couldn't make a statement about anything else from there. But the two triangles are congruent, so these are corresponding features. So look, it's the median. Well, these two angles are corresponding, so they're the same angle. Well, this is a straight angle, so that means these have to be 90-degree angles. So look, it's also an altitude, but it's also the perpendicular bisector. So it's all four of the auxiliary lines are the same line in this case. Okay, now, but we talked about how if we drew these auxiliary lines coming from one of the base angles, then in general it's not going to work out this way, that they're all going to coincide like that. But for the case of an equilateral triangle, an auxiliary line coming from a vertex, you're always going to have that isosceles triangle setup. So, okay, if we started with these two sides are congruent and we drew an angle bisector coming from Z, well, then there you go. So that means that the angle bisector is the median, is also the perpendicular bisector, is also the altitude, right? Well, for an equilateral triangle, if we draw auxiliary lines coming from this vertex, well, look, we've got two congruent angles again. So this line is going to be the median, the angle bisector, the perpendicular bisector, and the altitude. And same thing if we did auxiliary lines coming from here. So it's interesting how, you've got the equilateral triangle with these three lines of symmetry here. It's very symmetrical in that sense. But what's even more interesting is that so the equilateral triangle is from one perspective is very symmetrical, but this common point here is not a point of symmetry of the triangle. And you could see that if we look at this segment here. This segment is not the same length as this segment. You can see that visually. So there you go. It's not symmetrical about this kind of center point here. Okay. Now, the next thing they talk about is the idea of the perimeter of a triangle. The perimeter of any figure, I mean, let's stick with polygons at the moment. The perimeter of any polygon is just the sum of the lengths of all the sides. That's it. Doesn't matter if you have, if the polygon has side lengths that are the same length, different lengths, whatever. If you sum all of the lengths of all of the sides, the value you get is the perimeter of the polygon. So in regards to triangles, if you have a triangle with side lengths A, B, and C, then if you sum those lengths, that's what you get to be is the perimeter. The perimeter P. That's it. That's it. This is just a definition. It's just a property of triangles. So, okay, with that, it says given that angle A here is equal to, or angle B here is equal to angle C, okay, and that the length of AB is 5.3 and the length of BC is 3.6, find the perimeter of this triangle. Well, okay, because we have these two congruent angles, that means that the side lengths opposite these angles are the same. It's isosceles, so B is equal to C. Okay, so AB is equal to lowercase c, and it's equal to 5.3. So that means lowercase b is equal to 5.3. So we've got 5.3 times 2 plus 3.6 is the perimeter. All right, this next example says the perimeter of triangle ABC in the previous figure is 47. So they're giving us the perimeter. If AB is equal to x and AC is equal to x plus 1 and BC is equal to x minus 5, find x as well as the length of the sides. So this is kind of confusing because they want us to reference this figure, but these two angles in that case can't be congruent because we have a scalene triangle here. The side lengths are all different, so it's kind of confusing. They're suggesting that we're not starting with, we weren't given that the two angles are congruent, so we don't have congruent angles. So, all right, but if the perimeter is 47, then, well, what is the meaning of perimeter? We just add up the lengths of all the sides. So x plus 1 plus x minus 5 is equal to 47. So 3x minus 4 is equal to 47. 3x is equal to 51. So x is equal to 17. So that's x. And now to get the side lengths, just, so AB is equal to 17. AC is equal to 18. BC is equal to 12. So that's the idea of the perimeter of a figure in general. You're just adding up the lengths of all the sides. But really at the moment, let's just focus on a 2D figure in a plane, and let's focus on polygons. You just add up all of the side lengths of the polygon, even if they're not the same length, and that's the perimeter of the polygon. Now, the idea of extending the perimeter to 3D figures and other kinds of figures, that's a separate discussion. Right now, just focus on that. The perimeter of a polygon is you add up the lengths of all the sides, and you get the single value. That's the perimeter. And a triangle is a polygon, right? So you can think about the perimeter of a triangle. Okay, so now they just give this table of properties that we've learned about triangles in previous sections and this section as well. So let's take a look at this. This will be like a refresher. All right, so you have a scalene triangle, means that no two sides are congruent. Okay, now if we think about the scalene triangle in relation to the angles, the only really property is that the sum of the angles is going to be 180 degrees. That's really it. That's all we can think about. But we can also think about the fact that, well, it's probably the case that a scalene triangle is not going to have any angles that are going to be congruent. Because if there were two angles that were congruent, then it must be isosceles. If there's three angles congruent, then it must be equilateral. So that's not an official proof. That's more of an informal statement, but it seems that that's the case, that if you have a scalene triangle, then the angles, you're not going to have any congruent angles as well. Okay, in an isosceles triangle, you're going to have just two angles are congruent, not three, because then you're going to call that equal angular. So just two are congruent. So in that case, the sum of the angles is still 180. That's the case for any triangle. But in this case, you have two congruent angles. So you can just like take one of the angles and multiply it by 2, add it to the third angle, and that's 180. Okay, an equilateral triangle, which is we know now is also an equal angular triangle, means that all the angles are congruent and all the sides are congruent. That's the same triangle. And since the sum of the angles of any triangle are 180, that means that for an equal angular triangle, the angles must measure 60 degrees, all those three of the angles. Okay, an acute triangle we know means that all of the angles of the triangle are acute angles. Okay, now in this case, in regards to the sides, it says possibly 2 or 3 congruent sides. So you can have, we saw an equilateral triangle is an acute triangle. All three of the angles are congruent, right? We can see here visually this isosceles triangle looks to be acute. And we saw this scalene triangle looks to be acute as well. So an acute triangle could be equilateral, could be isosceles, could be scalene. And so with that then, when it comes to the angles, same idea. You could have any one of these three relations between the angles. Okay, a right triangle is a triangle to where one of the angles is 90 degrees. Only one. You can't have two angles be 90 degrees. That would mean the third angle is equal to 0. That wouldn't be a triangle. So a right triangle is to where one of the angles is 90 degrees. Okay, in this case, you can have an isosceles right triangle, or you could have a scalene right triangle, but based on the Pythagorean theorem, we can see that we can't have an equilateral right triangle. Because in that case, to make this formula work, one of the leg lengths would have to be equal to 0. Okay, so when it comes to the angles, you're always going to have two, the 90-degree angle is going to correspond to two acute angles. If it's equal, if it's an isosceles right triangle, the other two angles are going to be, the acute angles are going to be 45 degrees because they have to be congruent. If you have an isosceles right triangle, that means the legs are going to be the equal pairs, not the hypotenuse. And so therefore the angles opposite those legs are going to be the two congruent angles. And so if it's a right triangle then, and the two other angles are congruent, then that means that those angles must be 45 degrees. That's the only way it would work. Also, we saw that the acute angles are complementary. They have to be, because they have to add to 90 so that you have the right angle plus the sum of the other two angles is going to be equal to 180. All right, now last we have an obtuse triangle where one of the angles of the triangle is obtuse. And it can only be one, because then it wouldn't make any sense to have more than one obtuse angle in terms of the summing to the angles to 180. So here in this case, we can think about how it's possible to have a scalene obtuse triangle. It's possible to have an isosceles obtuse triangle, but it's not possible to have an equilateral obtuse triangle, because it's for the same exact reason here, that the right triangle couldn't be equilateral. This is even a worse case of the right triangle as far as why this can't be equilateral. Okay, and so similar to a right triangle as well, with that obtuse angle, that forces the other angles to be acute.